sometime later this semester we're going to talk about a particle in a box. So let's imagine you have one particle, let's just say an electron. We're going to confine it to a box of length equal to 1 nanometer. Okay? If we solve the Schrodinger equation for that particle, you'll find, okay, that the wave functions, the eigenfunctions of the Hamiltonian operator would be of the form psi, okay, the nth eigenfunction, which will depend on x, is equal to square root of 2 over L times sine. You don't need to know this one at this point. We'll cover it later, but it's just so you can see what those solutions, what the time dependence looks like. Okay, so sine times n times pi times x over L. Okay, oops. And the function of time, what was it? So function of time for the nth eigenfunction is going to be equal to, you remember, e raised to the power negative iet over h bar, right? So I, the way you enter I in Mathcad is you type 1i. Okay, if you just type I, Mathcad doesn't know what that means. So you type 1i, that's the imaginary number, square root of negative 1. So 1i times e. Now e depends on the which quantum state you're looking at. So e of n. So we're going to say e is a function of n. Okay, times t over h bar. So h over 2 pi, right? We can't do h bar on Mathcad, so we have to write h over 2 pi. Okay, and it's complaining it doesn't know what h is. So let's define h up here. 6.626 times 10 to negative 34 joules seconds. Okay, it doesn't know what time is. Oh, this is a function of time. Okay. Okay. And it doesn't know what E is. So let's define the energy. It turns out in this case, the energy for the nth state. Okay, if you solve the Schrodinger equation, you'll find that it's equal to n squared times h squared. Oops. H squared over 8 times the mass of the particle times L squared. Okay, so when we get to the particle in a box problem, we're going to see all of these. Now, it doesn't know what the mass is. You have to tell it what the mass is. What's the mass of an electron? 9.11 times 10 to the negative 31 kilogram. Okay, and L. Let's just tell it what L is, because it's assuming what L is. L is a predefined variable, so I need to override that. L is 1 nanometer. Okay. And it doesn't know what a nanometer is, so I'll have to tell it what a nanometer is. A nanometer is 10 to the negative 9 meters. Okay? So that's what solutions are for the particle in the box. So if I were to plot from x equals 0 times L all the way to L. So I'm going to put 100 points in my graph. So 0.01, that's 1% of L would be the next point. Okay, and then semicolon allows me to specify the endpoint next. So I'm going to plot from x equals 0 to L. Okay, insert graph xy plot. What am I going to plot here? Versus x. And I'm going to do it in terms of L. And so I'm going to plot here psi of nx. It doesn't know what n is, so I have to tell it what n is. If n is 1, that's what it looks like. If n is 2, that's what it looks like. If n is 3, that's what it looks like. Okay? If n is 4, that's what it looks like. So those are your the time the part that's not dependent on time. Now, what's the overall wave function though? It's little psi times f, right? The overall psi. So let's define overall psi. So capital Y, control G makes it uppercase psi. Psi, the Greek letter, is Greek letter for Y. Okay. So this would be for the nth quantum state. This will be dependent on x and time, right? So this is equal to the part that depends on x, which is y, control G, and x, little psi. The part that depends on coordinates times the part that depends on time is f, right? F and comma t. So let me plot that one instead. Big psi for n equals 4. I have to specify x and time. Okay. What happened here? Yeah. Okay, now I have to put the units here. My units would be nanometer to the negative 1/2. Let me just redo this one. Okay, where did we miss? Big psi. Let's plot this from 0 to 1. And let's get a plot. I did define L to be 1 nanometer. And X, I define it to be 0 times L, 0.01 times L. Let me pause this video for now. Okay, I just realized that it's not really complaining about X over L. It can't calculate this because it doesn't know what T is. Okay, so I have to tell it what T is. So I'm just going to say T equals 0 for now. Since I'm going to do an animation, okay, I'm going to type T equals frame times, let's just do T equals 0 for now. Okay. There it is. Okay. And to be more specific, T equals 0 seconds, right there. So that's the same, basically the same thing. What happens at time 0? Basically, this f of t is what? E to the 0 is just 1, right? Yeah, I did start capturing the video again. So when time is 0, your big psi is just equal to your little psi, basically, right? So let's say for 1, let's go back right there. For 2, for 3, 4. Okay. Notice that what's the peak and bottom of your function? Your sine function goes from 0 to -1 to +1, right? So your minimum value is square root of 2 over L. Your positive value is square root of 2 over L. So this one right here is square root of 2 over 1, which is 1.4, right? And this one, the minimum is -1.4. This is if you have the right units, okay? If you don't put that unit right there, you're going to see different numbers here. So make sure you specify the unit you're plotting. Now, I'm going to make an animation of this. If you recall, e to the I, okay, if you have e to the I x, that's equal to what? Let's just call it IKT. Let's call this e to the negative I omega t. Okay, so what's our omega here? E of n over h bar, right? Now, anytime you have something like this, if you remember your Euler formula, this is cosine omega t plus minus I sine omega t, right? So this is going to be a sinusoidal function, except that it has a real and imaginary component. So if you were to look at what happens here, if I were to advance this time right here, let's say I make that 1 second, it can't show it on the graph because you have a complex number. So psi will not show up on the graph because it's a complex number. But what would happen if I were to take the square of this? Absolute value So I'm going to pick up the calculator toolbar right there. That's the absolute value. And then raise to the power 2. And you can see that's just the square of the function. Okay? If you don't, if you just take the absolute value, that will work too. And remember, what's the square root of 2 squared? Remember your peak was a square root of 2 over L, right? So if you square that, you can see the maximum is at 2. What would happen if I just took the absolute value without squaring it? And then it's just that, 2 over L. Okay? So it's 1.4. So that's the square, oops, the wave function, right? So what would happen now if I were to change my time? And I'm going to say, okay, what's the cycle time for the part that depends on time? Anytime you have a cosine or a sine function, it's useful, it's a function of time, it's useful to write it in the form 2 pi over tau. Okay? Because when your t advances by 2 pi, that completes one cycle. Okay, so you just need to figure out tau. Tau is the time it takes to complete one cycle. See, when t advances by an amount equal to tau, you see your cosine, your argument there advances by 2 pi, so that completes one cycle. And if you have something like cosine something times x, it's best to write your coefficient there as 2 pi over lambda. Because when x changes by an amount equal to lambda, you know the thing inside is going to change by 2 pi. All right, so I'm going to write it as cosine 2 pi over tau, okay? E to the I, 2 pi over tau. So I'm going to say your E of n here is equal over h bar is equal to 2 pi over tau. So what's my tau? Tau is going to be 2 pi h bar over E of n, right? And 2 pi h bar is just h. Remember, h bar is h over 2 pi. So h over E of n. So I'm going to cycle my time from 0 to tau. So I'm going to calculate, I'm going to generate an animation of this graph with my time advancing from time 0 to tau. And my tau is h over E of n. Okay? So here's what I'm going to do. I'm going to define tau, the cycle for my period, for my cycle, for my function of time. For the nth quantum state, it's going to be equal to h over E of n. All right? So I'm going to let this cycle through. So I'm going to define my time instead using a frame variable. Frame times 0.01 times tau of n. Okay, since I'm going to plot psi 4, so I'm going to say tau of 4. Okay, tau 4, the period for n equals 4 is, that's not 0 seconds, it should, let's set our 0 tolerance to a smaller number, so that's going to be 10 to the negative 16 seconds, okay? That's 0.6 femtoseconds. So I'm going to advance my time from 0 all the way to tau for this one, okay? So let's see what happens here. In addition to this, I am going to plot the real part of psi, okay, for xt. And what's the unit for psi itself? Close parenthesis. Nanometer to the negative 1/2, right? And I'm going to plot the imaginary part of psi for xt. And my unit is nanometer to the negative 1/2. And there it is. Notice the red curve is psi squared, right? And the blue curve, this is the real part of psi, okay? And the green curve is the imaginary part of psi. Okay, at time 0, what do we notice at time 0? At time 0, this part is 0, right? So everything is real. Well, as time advances, you're going to see your imaginary and your real parts are going to change. Okay, so now I'm going to put here, I'm going to put a little space here, and say t equals, I'll put this in terms of tau, okay, tau of 4, okay, so I'm going to animate this, view, animate, I'm going to do 100 frames, so since I'm going to step it, each frame will step it 1% of a period, 100 frames will give me one entire period, okay? And then I'm going to, select this section to animate, hit animate, okay, and there it is. So look at what happens to the real part, which is the blue curve, okay? Look at the blue curve. It's changing. The value at any given point is oscillating in time. Okay, look at the green curve. That's the imaginary part. It's also changing. Okay, it's going through cycles. But look at what happens to psi squared, the red curve. The probability density function is not changing. Okay, so your real part and your imaginary parts are changing, but your overall probability density function, the square of your wave function, is not changing. That's why we call it a stationary state. Okay? So let's try one more thing. And this time we're going to plot psi. We're going to say, let's say psi, big psi, happens to be for a particular state. So let's say an actual psi. Okay? I'm just going to say A, so I don't have to type the whole word. So function of x and time. Let's say it's equal to a linear combination of psi 1 and psi 2 and psi 3. Okay, so let's say it's 1 over square root of 5 times psi 2. So it's going to be y, control G, psi of 2xt, right? Minus 2 over square root of 5 times psi 3. So y, control G, 3xt. Okay, what will that look like? Insert graph, xy plot. Okay, so I'm going to plot versus x over L. And I'm going to plot psi, this the actual psi sub A as a function of x and time. And that's what that plot looks like. Okay, at time 0. And so I'm going to advance my time. I'm just going to go again. Same thing, frame times 0.01 times. I'm just going to use the period for tau of 4, okay, for n equals 4. And I'm going to say t equals something times tau of 4. Okay. What's going to happen to my psi if I change my, okay, I'm going to put this in terms of the right unit. So what's the unit for psi? Nanometer to the negative 1/2. Right? And so I'm going to set my axes to go from, let's make this negative 3 to positive 3. Right. So I'm going to do that for my psi. So I'm going to square that. So absolute value square. Okay, so that's my probability density function. Let's make this 5, -5. Okay? And so what do I need to do here? I want to show you the real part of psi, the actual psi as a function of x and time, right? And my unit for that is nanometer to the -1/2. And that's the real part, comma. And the imaginary part would be capital Y, control G, dot A, xt, over nanometer raised to the -1/2. And there's your imaginary part. When time is 0, okay, then you don't have any imaginary part.
What was the difference between RE and I?
Yes, those are predefined functions in Mathcad. RE is the real part of a complex number, and IM is the imaginary part of a complex number. So now let's do an animation. View animate. I'm going to do 100 frames. And let's see what happens. Let's make that 200 frames. Just so we have a little bit more. Alright. So let's look at the blue curve. That's the real part. I'm going to play it. You can see the real part is changing. The imaginary part is changing. But look at the red curve. The red curve is a square of psi. It is changing. This is not a stationary state. It's a linear combination of non-degenerate stationary states. It's a solution to your time-dependent Schrodinger equation, but it's not a stationary state. It's not a solution to the time-independent Schrodinger equation. Okay? So, and you can one thing you could do is maybe calculate if you have a lot of these, it's possible for those waves to add up so that you have a very steep packet, you localize your particle into like a little packet here, so you have a higher probability of finding the particle in one particular region. And so that would be a way like you can track sort of the movement of the particle where there's a high amplitude of psi, there's a high value for psi squared. Okay? So I think that's all I got.